Welcome everyone to the morning session of the workshop today. The first speaker is Ying Zhao from UC Santa Barbara, and she will tell us about collisions of shock waves and the quantum circuits. So please start.
Okay, thank you. So first, I want to thank the organizers for giving me the chance to speak here. And today I will talk about collisions of shock waves and quantum circuits. It's based on some recent work with Felix, Gary, Henry, and Lionel. So first, I want to give some background and motivation. So to this, by the way, the talk is 45 minutes plus 15 minutes, right?
Yeah.
Okay.
But so, you can if you want you can use spend the time as long as it is within the 60 minutes. So yeah, don't tell me that feel constrained.
Okay, good to know. Thank you. So first, some background and motivation. Two distant black holes can be connected in the interior through a wormhole. And such an Einstein-Rosen bridge can be interpreted as an entangled state. And this is the famous statement of ER equals EPR. And here's a Penrose diagram. And you'll see that from Penrose diagram, you'll see a feature that within such a space-time, if you're jumping from both sides, then there is a chance that you can meet in the interior. And so this is a mysterious feature because there are no boundary interactions between the two sides. So one can ask, what governs the law according to which the two signals interact? And in this talk, we will attempt to answer this question from the point of view of quantum circuits. Before I start, I should point out that recently there are some very interesting work also involving black hole interior, but they studied black hole interior from point of view of operator algebra. So here is a cartoon picture, a quick summary of the basic idea. What I draw here is that the horizontal direction is time direction. The vertical direction is space direction. And this is saying that I think will be clear later. It's when you send in a signal, there's certain perturbation that grows in spatial direction. And in the left panel, the growth of these two perturbations, they do not feel each other because they don't have overlap. And in the more interesting case is the right panel. The two perturbations, they actually overlap. They do feel each other. And as we will show later, that the interpretation is that the two signals somehow interact gravitationally. So here's the outline of the talk. We will discuss the meeting in the interior of the wormhole and overlap of perturbations in the quantum circuit. We'll discuss collisions. First, look at collisions between spherically symmetric shock waves in ADS-sized black holes. Then we turn to collisions between localized shock waves. At the end, I will point out some future directions and unanswered questions. So first, some background. Bok tensor network and quantum circuit. It's well known that the Bok geometry reflects, so within the context of ADS-CFT, the Bok geometry reflects the minimal circuit preparing the state. And so here's the quantum circuit, and this is the time direction. As time increases, the circuit gets longer. These orange dots are quantum gates, and this is just a particular toy model of quantum circuit. And you randomly pair, these black lines are qubits. You randomly pair up these qubits, and you apply gates, two qubit gates on each pair. This is just a particular toy model. But the point is that it gets longer as time increases. Why? Because the dynamics of a black hole keeps going on, and so the quantum circuit gets longer. The quantum circuit, in this case, is a record of the dynamics. And on this side, the interior is getting longer. There is a key property in this particular setup, because in this case, we represent this, let's say, thermal field double by, let's say, S is the black hole entropy. We represent this by S Bell pairs. Once you have Bell pairs in your lab, you can apply, let's say, Bell pairs shared between A and B, Alice and Bob. You can apply unitary gates on Alice's end, or you can apply unitary gates on Bob's end. but these gates can be undone from either side. So when Alice applies certain gates, and let's say Alice applies some gates in her lab, and then she left her lab, and then Charlie comes in and look at Alice's system, he won't notice that Alice ever applied these gates. Why? Because these gates actually can secretly be undone by Bob. Another way to say that is that these gates doesn't change Alice's density matrix. So there's a in no sense, these gates, all these orange dots, there's a no in no sense it belongs to A or it belongs to B. It's only these orange dots only is meaningful when you have a subsystem A and B together. And correspondingly, we see that the part of the wormhole that's getting longer is actually in this future interior. And it's a well-known fact that this is outside the entanglement wedge of A and also outside the entanglement wedge of B. It's only meaningful when you have subsystem A and B together. So we see that once you have entanglement, you can have a shared quantum circuit. And the rough idea is that once you have shared quantum circuit, then basically this shared quantum circuit basically gives you a stage that the two signals can interact. Let's go to a little bit more complicated setup. We perturb thermal field double, but we look at ADS-sized black hole. So we represent the perturbation by something so-called an epidemic model. This red arrow represents the extra qubit due to, let's say, Alice is the left side, Bob is the right side. This red arrow represents the extra qubit due to Alice perturbation. You might ask that why do I introduce the extra qubit? The reason is that the perturbation increased the black hole's coarse grain entropy. So we just represent this increase of coarse grain entropy by this extra qubit. And from this toy model, any qubits that interact directly or indirectly with the perturbation will get perturbed relative to the original circuit. So I appended in red here. All these qubits now are affected by this red guy. And because all these qubits and all these gates are affected by this extra guy, and they can no longer be undone from the right-hand side. They can only be undone from the left-hand side. But for the purpose of this talk, actually, I will mostly focus on these orange gates. Notice that because the dynamics is k-local, when I say k-local, I mean at each time step, each qubit only interact with the k other qubits, where k is order one number. This is modeled from properties of a matrix model. Because the dynamics of is k-local, this perturbation takes time to spread. That means even after the perturbation comes in, there are still healthy gates left. Even after the perturbation comes in, there are still a large number of gates that can easily be undone from Bob's side. So because this thing spreads like an epidemic, so these things that are unaffected, we will call them healthy gates. And correspondingly, if you look at a Penrose diagram, this after the perturbation comes in, there are still space-time region here, which is shared between Alice and Bob. And we will identify this part, this orange region, with these gates, which are healthy gates, but it's on the left-hand side of this perturbation. This is the key property we'll keep using. And notice that this crucially depends on the fact that black hole dynamics is k-local. And what we're really interested in is gravitational interactions. When we have what will happen when we have two signals. And when you have two signals, and when you draw the quantum circuit, you have, let's say, one signal comes in from the left, the other signal comes in from right. You make one perturbation grow to the left, the other perturbation grow to the right. And you just draw the picture, quickly notice that there are two possibilities. One possibility is that you can arrange the time such that there are no overlap between the two perturbations. I mean, there's no time in the circuit where the where both perturbations appear together. And correspondingly, the two signals will hit the singularity before they have a chance to meet. Of course, we are more interested in the case when they do meet. And what will happen is that you can arrange the time such that there is overlap in the circuit. So in this part of the circuit, both the red perturbation and the purple perturbations appear. And correspondingly, the two signals meet in the black hole interior. That's the proposal. And it should be intuitively clear that the larger the overlap is, this is overlap region, the larger the overlap is, the stronger the collision is. We will make this more precise. And actually, one can diagnose if the collision happens or not by looking at the size of operator preparing the state. The computation reduces to certain 6-point functions, but I won't talk about it in today's talk. And in today's talk, I mostly want to characterize their gravitational interactions. And on the bulk side, on the gravity side, I want to ask about the properties of geometry in this region, the post-collision region. And the properties is clearly encoded on how these two things overlap. And recall that when you have one perturbation, the healthy gates after the perturbation comes in is stored in this shared interior region. So now you have two perturbations. Let's look at the healthy gates in this overlap region. So they are healthy, so they must be in the shared interior. And they are in this overlap region, so they are behind both signals. And we will identify the healthy gates, the orange dots here, the healthy gates in this overlap region with the post-collision region. That's the basic idea. It's like we identify different sorts of gates with different subregions. And when we want to ask about properties of different subregions, and we look at the properties of those gates inside the quantum circuit. That's basically the logic, the rough idea, and we'll just apply this idea and see what we get. Is it clear so far? Are there questions?
There's one question.
Yeah.
Sorry, I'm a little confused about what these perturbations are. Are they essentially taking you from unitary dynamics to open system dynamics by interacting with...
It's a unitary. It's okay. I see why you ask open system dynamics, because I introduced extra qubit. But what happens is that when you really have in the context of ADS-CFT, you just apply a unitary operator on the boundary. So it is unitary dynamics. And at the level of toy model, I represent things like this. I represent this system by S-Bell pairs, plus a lot of extra degrees of freedom that are not entangled. And what we did is that we excite one of those unentangled extra degrees of freedom. So it's unitary dynamics.
I guess then the thing I don't understand, if it's unitary dynamics, you can undo it as you wish.
Okay. The key property is that this extra guy, let's say when you introduce extra guy, forget about this purple thing. Let's just look at this red thing. This red thing can be undone from left side, but not from right side.
I see.
Because the right system has no access to this extra qubit.
So you're including not just unitaries, but isometries and co-isometries, correct?
I still treat this as unitary in the sense that I imagine my system including certain number of Bell pairs with plus some unentangled degrees of freedom, and it's a unitary on this Bell pairs plus this unentangled degrees of freedom.
I see. I understand now. Thank you.
Okay. Thank you for the question.
So I have a dumb question as well. So okay, according to this Maroff-Max, the Maroff wallpaper, the collision in the black hole interior belongs to the super selection sector with respect to the CFT algebra. Well, why can you detect this collision from the CFT point of view? So sorry, I understand this is a dumb question, but
No. This is not dumb question. It's a very good question, and because I thought the point of that paper is basically to I might misunderstood that paper, but I thought is that basically would say that no, you cannot. It's basically say that if you are not in that super selection sector, then basically the two things cannot meet. Which basically I disagree. I would say that thermal field double. When you do have thermal field double, then it's due to a space-time like this. Yes, they can meet. And when you have both left and right system, when you have both systems together, you can actually cook up something to detect that if they meet or not.
I see. Okay.
So they point out that it's a puzzling feature, but I'm not sure I really agree with their conclusion.
Okay, I see. Thanks.
Thank you for the question. And for the rest of the discussion, as we said before, it's intuitively clear that when the overlap gets larger, the collision gets stronger. So everything will be the property of this overlap. We'll call delta T here. It's the definition. I think it's obvious from this picture. And let's first do some quantum circuit analysis. So for purpose of later discussion, we will consider the case where the scrambling time for the two signals are actually different. This will make the discussion more interesting. And the way we make it happen is that we make the initial perturbation to have different strength. Let's say in the left-hand side, we throw in 1 extra qubit. On the right-hand side, we throw in square root of s extra qubit. Note that square root of s is still much less than s, so relative to the black hole is still a small perturbation. But because of this, roughly speaking, the scrambling time of the first guy will be twice of the scrambling time of the second guy. And so here's the picture. When they don't meet, this is what will happen. And also from now on, I will stop drawing this kind of pictures. I will just draw this kind of pictures. I think the meaning should be clear. And there are 4 different regimes. The first regime is that when delta T is small, when you draw a picture like this, clearly you see that when delta T increases, the healthy gates, which in this picture is in this white region, the white region will grow. Roughly speaking, the white region grows linearly in delta T. There will be an interesting regime when the two scrambling times are different. You actually have a regime here. You see that in this case, when you change delta T, this gray part, this overlap so this healthy gates in the overlap part, this part actually no longer depends on delta T. So whatever we're interested in this quantity, what this corresponds to in the gravity part, and this actually becomes time independent. Later, as you make delta T larger and larger, you'll see that this region actually starts to shrink. It, roughly speaking, shrinks linearly in delta T. And clearly, there is a very sharp transition. I will comment this towards the end of my talk. There is very sharp transition here when delta T is larger than T star 1 or T star 2, roughly speaking, twice of scrambling time. Basically, you no longer have healthy gates. So this is what you see from circuit analysis. The question is, in gravity, what does gravity do? And I can tell you that from some concrete calculation, one can show that gravity indeed reproduce such features. Roughly speaking, on gravity, there are 2 effects that they are competing with each other. Here's the one effect. If you ignore back reaction, just imagine these 2 signals propagate on a fixed background. Then, as delta T increases, this point is going down. And as this point going down, this post-collision region will grow. And so in this first regime, the first effect dominates. The second effect is that as the collision becomes stronger and stronger, you can actually no longer ignore the back reaction, and the singularity will start to bend down. The singularity bending down will make the post-collision region shrink. And this second regime is exactly the time, the situation when the two effects actually balance out each other. So this point is going down, but singularity is also going down. The two effects balance out each other. The third regime is like, let's say the third and fourth regime is when this point is already very close to the horizon. So this point no longer moves, but the singularity keeps going down. So this region shrinks. And eventually the singularity is so close to this point, it's just everything stays exponentially small in delta t. So we can do some concrete calculations. Let's say in BTZ geometry, we can do both circuit analysis and can do some direct computations in gravity. And here is what we get with the various different parameters. I think on Zoom you should be able to see that each line is secretly two lines. One is a straight line. The other is one is solid line. The other is dotted line. The solid line is from circuit analysis. The dotted line is from gravity calculation, and you'll see that there are four regimes. First, the linear increase. Then there is a plateau, the second regime. Initially, I was worried about this plateau because when I noticed there is a plateau regime in the circuit analysis, I was wondering if gravity will be able to reproduce that. But somehow, yes, gravity just reproduces this feature. Gravity also shows a plateau, and then linear decrease, then stays exponentially small. These are just with the different parameters. You can see that so this is the space-time volume, post-collision region space-time volume as a function of delta t, and you see pretty good match. So far is the spherically symmetric case. Are there any questions? Okay. Now let's move to.
So could you say a few words on this epidemic model you were talking about? Is it are you going to mention about it or?
Actually, I won't. But if you ask, I just want to say that the circuit model we use is really simple. Let's say we have S qubits, and at each time step, we pair them up into S/2 pairs, and on each pair, we apply a randomly chosen 2-qubit gates on each pair. And this epidemic model is just imagine someone carries some epidemic and comes in and will interact with randomly, let's say, first interact with this guy and this guy gets sick. And then the two of them will interact with other people. Now the 4 people got sick. Is a toy model like this. This model is really naive. You might be surprised that how could a really naive model like this being able somehow the match with gravity can be so good. I was surprised until I understand that there are certain key features here that exponential spread and saturation after scrambling time. Basically, various properties just depend on these two key features. This model is really naive, but it managed to capitalize these two features. Things spread exponentially in time, and because the black hole has finite entropy, it takes scrambling time to saturate, and that's why it's somehow, it ends up matched with gravity computation pretty well. There is nothing miraculous about this particular model. It's really simple. As I said, it really is the feature of k-locality of gravitational interactions guarantees that this kind of, once you send in your perturbation, its effect grows exponentially in time.
I see. Very interesting. Thank you.
Thank you.
Sorry, I have a very elementary question. So you have this plot. I think you said it's space-time. Yeah, space-time. Is this space-time volume in?
Yeah, is this space-time volume? But the reason we computed space-time volume because space-time volume is easiest to compute. And actually, in BTZ geometry, there is another big. So, but this is not the first quantity I computed, because in BTZ geometry, as is well known, that singularity is not really singular. The first thing I computed is just the proper length of the segment in the post-collision region. The first time I computed is just this length in BTZ geometry. They actually shows the same time dependence. So what this quantity characterizes is really it's a characterization of the growth of this particular region. Space-time volume is just something that's easy to compute and can quantitatively characterize how large this region is.
I see. So what you plot is this shaded region. So volume.
Yeah, it's a property of this shaded region. I need a quantity that characterizes the property of this, the growth and the shrink of this shaded region.
And but why you have this saturation? So you see your graph shows increasing and saturation and going.
Yeah, the saturation. Do you understand it from the circuit side? Why is there a saturation? Because just look at this picture. Can you see my cursor?
Yeah.
You just look at this picture and imagine that you move delta t, and you see that this part is controlled by t star 2. This part doesn't depend on delta t.
T star 2.
If you look at the first picture, clearly when delta t changes, this gray region will change, right?
Yeah.
But in the second picture, this thing barely changes.
I see. So T star T, how did you decide it's T star?
This T star is the scrambling time of the second signal.
Okay.
Yeah, it's I chose a parameter such that the scrambling times are different, such that the scrambling time of this guy is less than scrambling time of a first guy. That's why you actually have a plateau region. If the two scrambling times are the same, you actually don't have a plateau region. But it really surprised me and make me happy, make me excited that somehow gravity computations reproduce this plateau region. So when you do gravity computation, you indeed find that in certain regime, the space-time volume doesn't depend on delta t.
So for gravity side, naively, I think it's very monotonically. I expect some.
Yes, exactly.
But
so
it's
this
not so clear why you have a.
So this regime should be clear that if you ignore back reaction, this part just goes down, and then this post-collision region just grows. This is the obvious part, right?
Yeah.
What's not obvious is that because of the back reaction, the singularity actually bend down.
Okay.
This requires computation.
Okay, that's
from the back reaction. So it's a bit surprising that this silly circuit model somehow knows the back reaction of gravity.
I see. Thank you very much.
Thank you for the question. I mean, I really appreciate all the questions. I mean, I'm not in a hurry to go towards the very end. I would rather everyone to really get the core idea here, and how much we cover. It's what's left is mostly details, generalizations, more calculations. It doesn't matter if we go through them or not. I would rather to have more this kind of discussion and make sure everyone get the key idea. So if you have questions, please ask. So.
Sorry, can I ask
a
question?
Go ahead.
So what is the solid line in that plot?
So this plot?
Dotted line seems to be a volume, but so what is a solid line?
The solid line is circuit analysis. It's the number of healthy gates in the overlap region. So let me go back to a picture of a quantum circuit. Okay, so let's say you have a picture like this. You can count the number of orange dots in this overlap region, just through a naive epidemic model. And actually, so there are better calculation is to using some 6-point functions, but without going into that details, I can tell you that it's just you can just do some circuit analysis. You imagine you have one epidemic that spread in this direction, another epidemic that spread in this direction, and you assume they spread independently, and ask what's the probability of being healthy at one particular time, then do an integral over time. That's the solid line. That's from circuit analysis. It's a healthy gates in this overlap region.
I see. I see. So you calculate something in this circuit model. I see.
Yeah. So the rough idea is to somehow to study this gravitational interaction dynamics from the circuit analysis. That's the rough idea.
I see. I see.
From
Yeah.
qubit. Yeah.
I see. Yeah.
Yeah.
Thank you.
Thank you for the question. As I said, more questions are welcome. It's very helpful discussion. Okay, if there are no more questions, let's go to localize the shockwave case. As I said, I'm not really in a rush to finish everything. And so far, we only discussed the spherically symmetric perturbation, basically minimal sized black holes. For localized perturbation, it's analyzed in this paper. It actually came out much earlier in Tufts' paper, but these people give a quantum chaos interpretation. So on the gravity side, what happens is that the horizon jumps out, there will be shift. But in this case, the shift actually, it's no longer a constant shift. This shift will depend on transverse direction, which we call x. You see that there is a shift controlled by the time that this TWL is the time you send in the signal. The shift is controlled by how early you send in the signal, also depend on how far you are away from signal. XWL is the place of where you send in the perturbation, and this is for generic X. And in this paper, there is also a circuit picture. I basically redraw their picture. I basically rotated their picture and put it here. The key point is that there are two cones. One is this is a light cone, and as we all know that things cannot spread faster than light. If you apply perturbation here, all the effects will stay within the light cone. And this is the place where the effect starts to come in. But the point is that the signal will stays very small until it reaches the so-called butterfly cone. And let's say imagine you have the signal comes in here, and only after scrambling time it effects becomes big. And in generic dimensions, the two velocities are different. This is velocity 1. This velocity is different. And we are interested in collisions of two such localized shock waves. And we will focus on some particular x. And with the slight abuse of language, we will call the distance between the causal light cone and the butterfly cone T star. So we will call this T star. And notice that with this definition, the T star now becomes x dependent. And we again assume T star 1 is bigger than T star 2. Now you see that why earlier I insist on that the scrambling times of two signals are different. Because with localized collisions, generically the two scrambling times will be different just because the two cones have different slope. And this is just a simple expression of this guy and this guy. And what we do is that so from now on, we'll fix the impact parameter of the collision, but we will vary the time separation. The time separation, again, we call delta t, and we will see what happens. First, from circuit analysis, you easily see that there are similar 4 regimes. This first regime, the number of healthy gates here grows linearly in delta t. The number of healthy gates here now stays a constant. Now the number of healthy gates start to decrease linearly in delta t, and no more healthy gates. It's basically completely parallel with what we had before. The gravity analysis is more tricky because the metric in the post-collision region is in general unknown. And from circuit analysis, we see that there are 4 different regimes in general. What we do is we will try to identify different bulk features that are responsible for the different behaviors. First, let's look at the first regime, which is a linear growth. So assume localized perturbation coming at some finite time. The question is that where is the shock wave? And my first guess is that it's given by just u, where u is crucial coordinates, u equals constant. But this is not right. And actually, after a computation, some simple computations, you will find the following thing, is that it's basically the causal light cone. So if you let's say you go away from the source, and then what happens is that as if the signal comes in at a later time, let's say at the source XWL, the signal comes in at TWL. But when you go away from the source, it's as if the signal comes in at a later time. Not exactly, but almost. So the separation here is exactly our earlier definition of del T of X. So what we mean is that if you ignore back reaction, then this post-collision region is exactly controlled by del Tx. It grows linearly in del Tx. This is the first effect we discussed. If you can ignore back reaction, then the post-collision region grows linearly in del T of X. Now it becomes X-dependent. And as we said before, it's not exactly like this. There is some approximation, but in order to check if the approximation is good or not, we did some numerics. When we did numerics, you'll see that this plot is a plot, let's say, this overlap. As you vary x, you expect, as you change x, you expect it to grow linearly in x, then stays constant, then decrease linearly in x. And on the gravity side, if you ignore back reaction, this is exactly what you'll see. First, it grows linearly, then stays constant. We didn't draw the other half of our plot. It's basically the reflection symmetric. And as you change t, here is what you get. As you change t, you'll see that as you move this purple signal, this thing decreases linearly in time. You also notice that the slope of the first guy is twice of slope of the second guy. The reason is that in the definition of del T of X, X appears twice while T only appears once. So this is the first regime. Later regime, the other regime is more tricky because we do need to consider back reaction. So here's what we do. We will focus on this particular quantity. Notice that h of x is the shift at the horizon. And we will focus on the product of h1 of x times h2 of x. So you have a shift from the left signal, you have a shift from the right signal. And in 3D, that's exactly have this form. In higher dimensions, you have some power law here. But the crucial thing is that it depends exponentially on this combination. And this quantity characterizes the amount of overlap. So this quantity has a meaning in the circuit model. It characterizes the amount of overlap in the circuit at location x. And on the bulk side, this product controls the nonlinear effects of GR. So if we trust the circuit model, what the circuit model implies is that the singularity bends down and the shared region will become small at transverse locations x, where this product becomes of order 1. That's a prediction of the circuit model. And before we do any calculations, we want to say, one can see that this is a reasonable implication because when this guy is of order 1, this is exactly when nonlinear effect of GR becomes important. And it probably is not so helpful if I go through the details. I can just point out the rough idea. The rough idea is that when this guy comes in, there will be a jump of the expansion. So expansion basically characterizes how fast a family of geodesics shrink or expand. And because of gravity, actually, if you consider a family of non-geodesics, they actually shrink. The transverse directions decrease. And the rate of this decrease is defined as the expansion. What happens is that because of the matter comes in and the matter because of its gravitational interactions, there is a jump in the amount of expansion. And from the amount of expansion, you can estimate the proper time here. this proper time, the proper time to the singularity after the shock wave comes in. But you may immediately have objections because this proper time is a null proper time. It won't have any meaning. You are right. So what's meaningful is this: when you have two shock waves, and so this proper time depends on the normalization of certain affine parameters. Let's say depends on the normalization of this null vector. You pick two vectors such that the product of these two vector, I think is okay. I didn't use -1. I use -2L squared. You make sure this the product of these two vectors is -2L squared. With this convention, the product of this one times the product of this one and this one now is a physically meaningful quantity. With this convention, in spherically symmetric case, you can show that it's bounded by 1 over h1 of x times h2 of x. And so what do we have? We know that in the post-collision region, it's somehow the product of this direction times the length of this direction times the length of this direction is upper bounded. So it's quite reasonable that somehow the post-collision region is also upper bounded. And we need to use some ansatz because it's locally ADF3, so we use the following ansatz in the post-collision geometry. And basically, with this ansatz, and what we just assumed, we can reproduce the behavior of regime and 3 and 4. If we want to reproduce the regime for all 4 regions, we basically need to improve the bound we got before. I mean, this bound is based on the assumption that the shock wave comes in at a very early time. If we assume the shock wave comes in at some finite time, then you can improve this bound. Basically, the product of these two lines is upper bounded by something. Miraculously, it has the form of a sum over 4 exponentials. So a computation of 4 exponentials will give rise to 4 regime. And here is the plot. I think this is in d equals 3. This is for head-on collision. This is a post-collision space-time volume as a function of, this is x, this is the transverse spatial direction. This is the time direction. And so this is for signals with the same strength. This is the two signals with different strength. That's why you have plateau region. You can see that if you fix the particular x, then you just have linear increase, plateau, linear decrease, exponentially small. And as you change x, the entire plot is shifted. And this is for that earlier plot was head-on collision. This is for finite impact parameter. And I don't think I have time to go over to higher dimensions. Basically, you can just more approximation. I need to emphasize that this localized thing, there are some unjustified approximation here. So that's why we say that it's all we have is approximate bound. There is the unjustified approximation is here that we assume the ansatz of the post-collision geometry. What we checked is that with this ansatz, one can solve the geometry to linear order in h1 of x or h2 of x. And but the interesting behavior for us indeed happens in the case when the product of h1 of x times h2 of x is now too large. So I think in a regime where you see the non-trivial features of the plot, I think the approximation is good. Okay, sorry, I went over. So this is for the most, I just want to show the plot for the most general case. This is if in bulk dimension 5. And this is too complicated, but this is my favorite plot. This is for head-on collisions. And again, this is x direction, and this is the time direction. The reason this is my famous plot, this is my favorite plot, is because you can have a top-down view. This is a top-down view of this guy, and from the top-down view, you clearly see that there are two cones here. The two cones have different slope, and this picture very much look like the circuit the circuit picture I showed you at the beginning. There are two cones with different slope, but this is not a circuit analysis. This is a computation from GR. This is a computation from gravity. By studying the post-collision geometry, somehow we reproduce the two cones with different slope. That's why I like this plot. I can talk about some other applications, but since I'm mostly out of time, I think it would be better if I just give a summary and point out some unanswered questions and end the talk. And I really enjoy the discussion. If there are more questions, that would be nice. But before that, let me just try to finish. So there are some questions here. Is that basically we want to get a boundary interpretation of a bulk gravitational interaction. But one issue here is that what's the right bulk quantity to ask about? So when you talk about bulk gravitational interactions, I mean, obviously we are all very familiar with Newton's law, but Newton's law won't work here. We are talking about high energy collision. High energy collision was mostly discussed with S matrix. But in this case, the collision actually happens behind black hole horizon. So this is a regime that was not studied before. We don't even know what's the right quantity to ask about, because you don't have out states. So in order to define S matrix, you need to have asymptotic in states and out states. Here you don't have out states. How do you define S matrix? What's the right quantity to talk about? And so far we've discussed the space-time geometry after the collision. But this is not a very conventional quantity one usually uses to characterize a collision process. And can we make a connection between this and some more conventional characterization of scattering in a proper regime? The reason I list this is just for some future work. There is one special case pointed out to us by Matthew Hedrick, is that you consider Rindler ADS, for example, planar BTZ. From one hand, you can treat this as a hyperbolic black hole. So you can discuss the collision process as happening inside a black hole, in the black hole interior, and our discussion will apply. On the other hand, you know that the geometry secretly is just vacuum ADS. So unless you have a black hole formation, the signals will reach the boundary. So those more conventional quantities like S matrix, like correlation functions, still apply. So in a regime where you can study this collision by both ways, can one make a connection between there's two point of views? Another interesting regime to look at is as I said at the beginning, that from circuit analysis you clearly see a transition at two scrambling time when you no longer have healthy gates, and from a bulk point of view, what I believe is that corresponds to black hole formation. So I think in particular in 3D BTZ, black hole formation was exactly solved, I mean the case of from the collision of two particles, the solution is known, and in that case, one should be able to make a comparison with the circuit analysis. And so these are some future directions. And there are some other questions that's very important, but it's also more difficult. It's just I don't have any idea, just list here. The role of singularity. So far, I lied a little bit in the sense that what I said is only true when you have a space-like singularity. If you don't have a space-like singularity, for example, if you have a smooth inner horizon, then no matter how late you send in the two signals, they can always meet. So how to understand about the collision near the inner horizon for example, charged black holes. And what we see is that the dynamics inside black hole interior is somehow can be characterized by quantum circuit. And the idea I had in mind is that effective field theory physics in the interior more or less is encoded in this interior circuit. But we want to ask what will happen to the interior circuit when it becomes exponentially long. There are some very interesting recent work to show that at exponential time, this encoding circuit becomes highly non-isometric, and there might be some non-perturbative effects that becomes important. But from circuit point of view, what will happen to the circuit? We have been trying to understand matter propagating in the interior in terms of quantum circuit, but how ordinary matter, but how about firewalls? And at the end, I had fixed the Hamiltonian in mind in the context of ADS-CFT and how to incorporate different states of baby universes. These are some more difficult questions. It's just more conceptual. I just leave it here. And that's all I have. Thank you.
Thank you. Any questions or comments?
So in your head-on collision picture,
Yeah.
so the spread looks like faster than speed of light, or
It is a speed of light.
oh, it
This
is
one,
speed of light. Okay.
yeah.
Okay.
So this one has a speed of
So
light. This one has
the
a
other one
different
is slower than speed of light. Oh.
Yeah, so
Okay,
this
yeah.
speed is smaller than speed of light. This one is speed of light. It's just because x and t are used different scales. That's why it looks like
Thank you.
yeah.
Any other question?
Thank you very much for interesting talk. So I think we can also probe inside black hole region, inside the horizon regions by using complexity.
Yeah, that's another idea. Yes.
But your analysis, you talked about this volume, space-time volume inside this shaded region, and that analysis, reveals something, new compared with complexity.
I think you can use space-time volume to talk about complexity. The difference is that so here's the difference is that complexity normally talk about the complexity of entire states, and
Yes.
so that's why we worry about basically the entire slice, how the entire slice changes. And here, what I did here is that I focus on particular subregion, and I ask I basically was asking more detailed question. Instead of asking the overall what happens to the overall slice, I ask what happens locally here and locally that. That's why I basically need to do some other gates counting in the sense that I classify the gates. There are gates with this property, there are gates with that property, and ask what's the number of gates with different properties. It's just comparing with the earlier complexity discussions, we're asking more local questions here. As I said, using volume or spatial volume or space-time volume or certain geodesic distance at this level is really a matter of convenience. It's you can't using space-time volume to talk about complexity, but the key difference is that complexity cares about the property of this entire slice, how long is the entire slice. We care about local properties of what happens in this post-collision region.
I see. So maybe that's if we think some subsystem version of complexity, maybe very close to your analysis.
Subsystem.
Or it's not, but your case is not spatial region in the boundary safety. So usually we define
yes,
subsystem
exactly. It's not spatial region. Yeah, and from my point of view, that's why I'm interested in this. It actually involves the entire system. Because you are talking about it's not subregion. Because you are talking about so it is a subregion from point of view of bulk. It's a subregion of the bulk, but it involves the entire boundary system.
I see. So I see. The definition of the subsystem is completely different.
Yes, the subsystem is completely different. It's looks like it's a subregion of the bulk, but because it's deep in the interior, clearly you need the entire boundary system.
Yes.
Yeah.
Thank you very much.
Thank you.
So I have two questions.
Go ahead.
First of all, so your the definition of your the region bounded by two shocks.
Yeah.
The true may make sense in classical GR. Is there any quantum version of the definition? Because epidemic model side, that does make sense even in the presence of at the quantum level. So do you have any?
So I've been trying to do some calculations in higher derivative gravity, but I haven't really. It's something I have in mind. I haven't started the calculation yet, but that may not be what you are asked for. You are asking, let's say, what if the classical geometry breaks down?
Yeah.
Yeah. Then the answer is I don't know. If I'm allowed to make a guess, I would say that because the circuit secretly is discrete, you might get something qualitative similar to that. But other than that, I really don't know what to say when classical GR breaks down.
I see. Yeah. Okay. So okay. Actually, okay. So maybe I should say that okay, my goal is a little bit modest. I mean that okay. So just I mean that like an island formula. I mean okay. Let's just I mean include this. I mean that the bulk QFT effects, and then okay. So for example, like this RT surface is replaced by this QES, right? And
I see. So
yeah.
you want to consider quantum corrections to.
Yeah.
I see. There were discussions about quantum corrections to complexity, but I don't know. I would say at this stage, all I have is basically everything is a function of time, is a time dependence. So I assume if you introduce quantum corrections, it won't change the properties too much, but exactly how,
Of course. Yeah.
Exactly how, I'm not sure. That's a very interesting question. I would like to think more about it, but I don't have an answer at this point. Thank you for the question.
I see. Also, the second question would be that suppose that if we have a Python branch in the black hole interior,
yes.
Do you think this, I mean, the epidemic model side is also, the description of this epidemic model side also changed, or do you?
This epidemic, so, okay, that's an interesting question. You can ask what happens if you send in a shock wave with a Python's launch there.
Yeah.
And let's see. There is one particular example is that when you have a Cocola-Medicina type states, it's basically a black hole with the end of world brain, and you can certainly send in a shock wave there. I would say that epidemic model we have so far is the part that is strictly in the black hole interior. And in that case, the Python's launch is something sits inside, sits near the horizon. So from this point of view, it's not very sensitive to Python's launch. I don't know. I never studied a situation like this. I will think about that. But if I make a naive guess, is that the similar pictures will apply. It's the things will spread exponentially in time.
I see. Yeah. Thank you.
Thank you. They are all very interesting questions. I will think about them more.
Any other questions or comments? All right. So if not, let's thank Anne again for the wonderful talk.